Okay, we're going to cover two sections, 21.5 and 21.6. 21.5 is power in an AC circuit, and 21.6 is resonance in a series RLC circuit. So let's share the PowerPoint, and there's the PowerPoint. Now, if we have a pure capacitor, the potential energy, the stored energy in the capacitor is 1/2 times the capacitance times the delta V squared, delta V max squared. And in a pure inductor, the potential energy stored in the magnetic field is 1/2 Li squared, I max squared. And we've learned in the past that for a resistor, the average power is equal to the IRMS squared times the resistance. Now, we don't have pure inductors and pure capacitors, so there is a little bit of loss in these, but for the most part, we can consider it that there is no loss in a capacitor or an inductor, and all of the internal heating will take place in the resistor. So we know that the average power is equal to IRMS squared times R, and R is delta VR RMS divided by IRMS. So if we substitute that in for R, we know that the average power is equal to IRMS times delta VRMS, which is very similar to what we had in the well, it is exactly what we had in the DC case. Now, delta VR RMS is equal to delta V times RMS times cosine phi. Well, that cosine phi is what we call the power factor. So the average power is equal to I RMS times delta V RMS times cosine phi. And cosine phi, again, is the power factor. Okay, now, and that's pretty much does it for power in an AC circuit. Now let's go to resonance in a series RLC circuit. So the IRMS current is equal to delta VRMS divided by Z, by the impedance. So VRMS, which is VRMS divided by the square root of R squared plus X sub L minus X sub C squared. Now, when would this be maximum? Well, it would be maximum when X sub L is equal to X sub C. In other words, that's, if you can minimize the denominator, if it's just R, then you maximize your RMS, your current, your IRMS current. So we're looking for the case where X sub L is equal to X sub C. Well, we know that X sub L is 2 pi FL, and X sub C is 1 over 2 pi FC. So let's equate those. If we make them equal to each other, then X sub L minus X sub C will equal to 0. So we want to equate 2 pi F0 being the resonance frequency. 2 pi F0 times L equals 1 over 2 pi F0 times C. So if we solve for F0, we actually end up F0 squared if we take it to one side. So we end up with F0 equals 1 over 2 pi square root of LC. This will give us the frequency at which X sub L equals X sub C, and so you get 0, and Z ends up a purely resistive impedance. We can look at that. Let me change the share. Let's go to Mathematica, and let's see if I can Mathematica phasor diagram. Excuse me. Okay, so I intentionally I have here uh, a phasor diagram of a capacitor. There, the capacitor dominates, and you can see that the phase angle is negative. I can go positive, where the X sub C, X sub L dominates, and the phase angle is positive. But if I get it, and I forget what it's like 1162, and I think I'll just, I can slide it back and forth, and you can see that there's a point where the phasor is just lines up with the resistor, and I think if I recall, it's 1162. So I'm just going to type that in, 1162. And sure enough, that's where if you look at the V sub L, I don't know that you can see it on this scale, but the V sub L is equal to 110 volts in the positive direction. V sub C is 110 volts in the negative direction, and so they cancel out, and it's all on the resistor. So there's now for extra points. Show me the equation where I got 1162. That should be fairly easy to do. Okay, now let's look at. Well, let me go back before I show this. Let's go back to the PowerPoint, which is right here, and we're talking about resonance in a series RLC circuit. The current reaches its maximum value at the resonant frequency f sub 0. That is where X sub L equals X sub C, and all we have is a purely resistive impedance. So there is a point, the resonance is that point where X sub L equals X sub C, and they subtract. You can find it. You can find f sub 0 by solving for 1 over 2 pi square root of LC, and you can see that. Let's I believe that's it for, yeah, next is transformer, but we're going to go back to Mathematica here, and you can see that as I change the inductor, okay, that changes the resonant frequency. I change the inductor, that changes the resonant frequency. Let's put it somewhere in the middle. If I change the capacitor, that also changes the frequency. So that's our 1 over 2 pi times the square root of LC. That'll determine the resonant frequency. But now let's look at and see what happens when I vary the resistor. And you can see that the resonant peak becomes very broad as I go to like 1,000 ohms. If I make it very narrow, like down to 100 ohms, if I make the resistance small, it becomes very narrow. And that's something that we call Q. Right now, this Q, if you look in the red, Q is equal to 12. We can, as I go up in frequency, it gets broader, and Q is changing. I can get this up to about a Q of 20. Let's go in this direction. Oh, there's a Q of 26, very narrow, very sharp. And let's see if I bring that down there. Let's see, there we've got a Q of 34, very, very narrow. Well, what is Q? Q is where I don't know if you can see it, but the bandwidth is changing as we vary this also. So for a Q of 14, the bandwidth is 79 hertz. Let's take it all the way to the top. The Q 34.64, the bandwidth is 13. It's much narrow. And what the Q is, it's where a high Q is, or the bandwidth is determined where the peak, at the peak frequency, that is your reference, that's 0, and it's at the 3 dB points on either side. Minus 3 dB is the half power point. So it's the half power point on either side that gives you the bandwidth. And if it's For a high Q, that the bandwidth will be very narrow. For a low Q, the bandwidth will be broader. We can see like the, if we make it real low, let's see, there's a bandwidth of 4.4, I mean, there's a Q of 4.47, and the bandwidth is 79.6, 79.58. Okay, and I think that's it for the for this resonance talk. Wrong, oops, I need to stop the share this way. Okay, and I don't think they talked much about the bandwidth, so that's just extra. They may, I'll look in the text.